Our next speaker is Patrick McCreery, and he will tell us about accurate, precise, and homogeneous SDSS-5 exoplanet host star parameters across the whole sky.
Thank you. All right, I presume you can hear me all right? My name is Patrick McCreery. I'm a graduate student at Johns Hopkins University, and today I'll be telling you about accurate, precise, and homogeneous Sloan Digital Sky Survey exoplanet host star parameters across the whole sky. So to begin, I wanted to motivate this by considering keyboard. All right, not the space bar. Okay. I wanted to motivate this by, well, I apologize for the question being cut off a little bit, but how do we measure the composition of astronomical objects? So there are a few different ways that we could do this, one of which is using meteorites, which are essentially delivered to us, and we can measure their composition and properties so that we can understand something about the astronomical object that we are studying. Alternatively, you could send a spacecraft to, something like Saturn or Jupiter and understand the magnetospheres, the atmospheres, the rings, land on the surface of solid bodies to understand something about their composition or properties. And the third way could be to use spectroscopy. And that is using the light either transmitted through the object, emitted from the object, or reflected by the object to understand something about its composition or properties. And so if you were to consider looking at an extrasolar star that might host an exoplanet, meteorites might not be the greatest way to understand their composition because we don't get those. Sending a spacecraft is currently not viable for that and will not be viable. And so we're left with spectroscopy. And I would be remiss not to show this beautiful solar spectrum from NOAA lab that was taken on Kitt Peak. And you can see these beautiful absorption lines with very high precision. And if you were to collapse this into a one-dimensional spectrum of essentially infinite resolution and infinite signal to noise, you can see that there are absorption features from your favorite transition, such as from oxygen, carbon. This is just a small selection from around the 7,700 angstroms, 7,100 angstroms, and you can see that there are forests of transitions that let you know something about the abundance of these atoms in the star. So to move on to the Sloan Digital Sky Survey, it is an all-sky spectroscopic survey that includes the Milky Way mapper, the black hole mapper, and the local volume mapper. And for the purposes of this talk, I will only look or focus on the Milky Way mapper, which focuses on stars. It is situated, the spectra are taken in the H band with high resolution and high signal to noise. And this makes it ideal for measuring abundances of carbon, nitrogen, oxygen, and a plethora of other important elements that are perhaps useful for understanding exoplanet formation mechanisms. This is a 300 fiber spectrograph, so you're able to take many simultaneous observations with the spectrograph. And there are northern and southern counterparts in the form of the DuPont telescope at LCO and the Sloan Foundation telescope at APO. And so this provides a homogeneous way to get spectra of stars all across the sky, northern and southern hemisphere. And to illustrate this, this is a plot of all exoplanet hosts projected on the sky. You can see some common features like the Kepler field. And so the real priority of SDSS and one of the main goals of it is to understand the chemical compositions of host stars and stars that have been searched for exoplanets across the whole sky to try to understand in a uniform manner their abundances. And as an example, it has been proposed that the CO ratio is a good formation tracer for exoplanets. And this is just 1/2 of this quadrant that you can find in the classical Oberg 2011 paper. And on one side, if your exoplanet's atmosphere has a high metallicity, then you might, and a high C to O ratio, well above the stellar value, you might infer that the exoplanet formed inside of the H2O snow line. Whereas if you have a low metallicity and high C to O ratio, you might infer formation beyond the H2O snow line. This has plenty of complications that are highlighted, including one poster here today on the back corner from Eric, and I highly suggest you look at that poster. So moving on, if you were to look at the apogee ASPCAP abundances for dwarf stars in the SDSS DR20 sample, which is proprietary currently, but will be released in the next year. In the background, I have plotted a density plot of these abundances for, on the x-axis, your carbon abundance, and on the y-axis, your oxygen abundance. I have cross-matched with Gaia DR3 IDs, the exoplanet host stars that are in that sample, and then I've also placed in yellow the solar abundance. And you can see that there's a large dispersion in abundances. And so say you were to get a somewhat solar carbon abundance, this doesn't necessarily mean that your oxygen abundance will also be solar. So it's very important that you understand star by star the abundances and get a full picture of the carbon and oxygen abundances if you were to use this for, say, formation mechanism inferences. And to move on to fold this into a C to O ratio on the y-axis and metallicity on the x-axis, you can see there's no real trend in terms of C to O ratio with metallicity. However, you can see that solar is not necessarily the median. The red line in the shaded regions is the median C to O ratio in separate metallicity bins. And then in light blue there, I've plotted again the exoplanet hosts. So you can see that using solar abundances, or assuming solar abundances, might not be the most useful measure. And there's large dispersion here. And then I've also plotted nitrogen to oxygen abundances, and you'd see again that there is very large dispersion. And so the thing I really want to highlight with this talk is that using solar abundances is not necessarily the most accurate or precise, and and that understanding your star is truly important, as was highlighted in the beginning talk of the last session. And I also wanted to highlight a poster that I have. It's a virtual poster. But if you'd like to know more about work about constraining ages extremely precisely, along with stellar parameters and abundances, then come talk to me about that. Thank you.
Great, thank you. Questions? Okay, we have one in the back.
Hi, thank you. In the C versus O plot, what's the typical error bar?
On the
No, sorry, the C over H versus O over H.
This one.
Yes, what's the typical error bar there?
So on individual points, it varies a little bit, but it's something like 0.05 dex.
Cool. Okay, we have another question here.
Ilaria Pascucci, University of Arizona. Thank you very much. I have a comment actually.
Okay.
And I want to mention that the C2O ratio in the disk changes with time.
Right.
So we cannot just use the C2O ratio in the star to then connect to where planets form. Yeah.
These photospheric abundances are good proxies, but there are complications with these.
Okay, so maybe for me, I do have a question. So thank you for showing this planet host stars. So wondering if you can make some comment about what you find about the parameters for the planet host stars.
About the temperature, surface gravities
of the planet host stars?
Yeah, so Apogee does have the actual parameters as well. However, you can get these better by combining spectroscopy and photometry together to try to get self-consistent parameters. But I can talk more about that after it's a little complicated.
Thank you. We can take another short question. Okay, yeah, please.
Yeah, thanks. This is a really lovely plot. I'm wondering if you've thought about the differences between the C and O, this correlation between the exoplanet population of stars or the stars hosting exoplanets and those not hosting exoplanets. Seems like there's some information there.
Right. I mean, they largely overlap. I think it's a little hard to see the density plot behind this, but there is some sort of difference, and I think that might be expected to some extent. But there's a correlation, yes, between having an exoplanet and your abundances, yes. But I can talk more about that, about the details of the correlation.
Okay, in the interest of time, we'll move on, but let's thank Patrick again.